Okay, last video on graphing rational functions. So here we have the rational function h of x, and if you'll notice, the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, and what this results in is something called an oblique asymptote, and the oblique asymptote we can find by simply dividing by doing the division problem that is being this it's telling us to do. So like we're gonna I'm gonna rewrite the denominator as negative x plus 1. It's the same thing. And that's just gonna make it easier to do division. So I'm just gonna do I'm gonna do polynomial long division here. You can do synthetic division, but you'll have to remember. Well, actually, don't do synthetic division for a problem like this if it's given to you in a weird order, because there's something you have to consider, and it's not worth it because uh, long division is simple enough in this case. So the dividend is the numerator, and then the divisor is that rewritten version of the denominator, so negative x plus 1. And then if we actually do this, so negative x goes into the 2x squared, it goes in negative 2x times negative 2x times negative x is 2x squared, and then negative 2x times 1 is negative 2x. And then we're going to subtract this, which gives us 0, and then minus 1x, bring the 3 down, so plus 3. How many times is negative x going to negative x? It goes in positive 1 time. Then we got negative x, and then plus 1, subtract, and you get 0. You get 0, and then 2. And we don't care about this 2. What we care about is the quotient, and that quotient tells us that the oblique asymptote is going to be at y is equal to negative 2x plus 1. Now, I jumped ahead because I kind of wanted to point that out first, but we can get the domain of this pretty simply too, and that's, we have to actually consider that you can't factor that top polynomial. If you could, you would do that, and then if you can simplify the rational function, you would. If you were able to simplify it, canceling those factors would result in what's called a hole. A hole is just a different form of discontinuity. We're used to asymptotes at this point, but a hole is like a removable discontinuity where the graph looks exactly the same as it would otherwise. It's just missing one value. But this one does not have a hole because there's no canceling. So the domain restriction here of 1, the domain restriction of 1 is just an asymptote. It's just like what we're used to. So the domain of this would be everything from negative infinity to 1, union 1 to infinity. Again, it can't be 1 because if we plugged in 1 for x, it would be, the denominator would equal 0. And you can't have that. So that's the domain. We can't answer the range right now, so we'll come back to that. But the whole that one discontinuity, the reason that what that produces is a vertical asymptote. The reason the 1 in the denominator. So there's a vertical asymptote at x equals 1. Sorry, I did not say that very well, but I think you know what I meant. We just got done saying that there is no hole, so there's no hole. X-intercepts. So x-intercepts would occur when the numerator was equal to 0, or when the value of h of x was equal to 0. So we would go 2x squared minus 3x plus 3 equals 0 and attempt to factor this or use a quadratic formula or complete the square. But in either case, we would see that there are no real solutions, or there are no zeros to that polynomial, which means there would be no x-intercepts. There are no real zeros to that polynomial, so there are no x-intercepts. Y-intercepts, though, you could do that if you plug in 0 for x, that'd be y is equal to 0 minus 0 plus 3 divided by 1 minus 0. So there is a y-intercept at 3. Okay, now we can put this information on the graph and do that in blue dots. So there was a vertical, actually let's do these orange color for the vertical asymptote. There's one there at x equals 1. So oops, we're going to make this more thick. Oh, there we go, that's 2 c's right there. Okay, then we want to put in that oblique asymptote, which would be a line with a slope of negative 2 that goes to the y-axis at 1. So there's 1. and then I would want to like have another point there, and another point there, and another point there, another point there. And I'm gonna do a really bad job of drawing this line now, but it's a line that should look like this. Something like that. Okay, so wow, that's cool. So that is what we have. Then we can put those points on that with that one point, the y-intercept of 3 that we know about. It's right there. Okay, at this point we would have to go to a calculator to calculate what's going on. Well, we can actually, if we wanted to, right, we could plug in a couple of points. We can plug in, like, let's say if we plugged in 0, we would obviously we get that 3 out. If we plugged in 2, if you plug in 2 to this, you would get, I think, -5 out. So the point 2, -5 is also on this graph. And that's enough to tell us something interesting, that the data, I'm gonna see if I can do this and then erase it. But we could potentially have two different shapes here. We could have information like this, and then like this. Okay. I don't know why that just tried to draw 4 or 5 times. We could have information like that. I'm gonna delete that because it's not like that. Or we could have information inside, like inside the more narrow, the more acute angles, and that's what we have because we put those points in, so we know it's going to be like that. And if we drew it, it's going to look something like this. But we can't just assume necessarily where the minimum and maximum points are, because we have a whole bunch more questions to answer still. We want to know what the range is, when the function is increasing, when it's decreasing. So we really need to know if the minimum that's in this area right here and the maximum that's in this area right here, what the exact coordinates of those points are. So to do that, we're gonna need a calculator. So let's fire the calculator up, and we fire the calculator up and turn on, and I already have it entered into y equals. So if we graph that, it looks like this, and then we just do second calc to find a. Let's do the minimum. Let's do the max. Let's do the minimum first. Okay, so with minimum, that's to the left of it. That's to the right of it, and the guess would be right there. And so it actually turns out that that minimum is at 0, 3. So that's very nice and handy because you don't have to do any crazy other stuff. Sorry, screwing up over here. Then if I want to do the maximum, I just do the same thing. Second calc, go down to maximum this time. We're going to be to the left of the maximum, so somewhere in this area. To the right of the maximum, somewhere in that area, and then guess somewhere in the middle. And that one actually is at 2, -5, which is kind of the point we already sort of found just by just checking where stuff was. So that's also really convenient because we don't have decimals. Okay, so let's go back to this, and now we know we can find out a few things here. Oh, sorry, this was at 2, -5. So we can, wow. So we can state the range now. So the range is going from bottom to top, would be everywhere from -infinity to the -5, and that's including the -5 because that's on the graph, so it's part of the range. And then union, we'd pick up at that 3 and then go up to infinity. And again, it's including the 3, not including infinity. So that's the range. The interval when h of x is greater than 0, that's just when it's above the x-axis. So you can see that that's everything to the left of the asymptote. So how do you say everything to the left of the asymptote? Well, you say from -infinity to the asymptote, which is at 1, the vertical asymptote, that is 1, not including the 1. Then how would you say, then where would you say h of x is less than 0? Well, that's everywhere below the x-axis. So it's everything from the asymptote on. So we would say 1 to infinity, not including the asymptote. Okay, then when is h of x increasing? So increasing, that just means we would look for from here to here, it's increasing, it's going uphill. And from like here to here, it's increasing, it's coming uphill. So we got to write that in interval notation. So interval notation, that means we're going from the x-coordinate of that minimum, which was 0, not including it, because at the actual x-coordinate, it's neither increasing nor decreasing. So from 0 to the asymptote of 1, union, back from that asymptote of 1, and then up to the x-coordinate of that maximum, which was 2. I am not clicking this. I don't know what's going on. Buttons are loose. I don't know. So 2. Okay. Then when is h of x decreasing? Well, that's all the other part of this graph. It's like you're on a roller coaster. Let me just draw a little roller coaster car, very high fidelity here. Let's see. So we're like on the track right here. Is the wheels. And if you just set off from left to right, like it's going to be decreasing, going to pick up speed until you get to this point right here. Then we'd just go up the hill, click, 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 click. Then you'd come up the hill this way, click, 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 click. Then you'd get to the top of the hill here, and we'd start going downhill again. And then that would be also decreasing. So how do we say that in interval notation? It'd be so cool if this thing didn't keep moving slides. Decreasing everywhere from negative infinity to the x-coordinate of that minimum, 0, not including it. And then it decreases again from the x-coordinate of the maximum, which is 2, until forever. Okay, last thing here is the end behavior of this, and you can just do that, look at that by observing it. Generally speaking, when you have an asymptote, when you have an oblique asymptote, the end behavior will always be basically what I'm about to write here. But if you think about it, the bigger and bigger x values this way, the bigger x values this way. I can't see what I'm drawing, so hopefully that looks like an arrow. Man, y is just going to keep getting bigger and bigger, right? So we would say the limit this is unbearable. I'm just going to say it in words because I can't write it on this pen. The limit of h of x as x approaches negative infinity. I literally can't do it. Hold on. Maybe I can do it like this. The limit of h of x, here you go, h of x as x approaches negative infinity is equal to positive infinity. Or you could also say, this is the same thing as saying the limit of h of x as x approaches negative infinity does not exist. You can then, because you can't equal infinity, then the other end would be that the limit of h of x as x is approaching positive infinity, so it gets really bigger values this way. Obviously, it looks like h of x, or the y values, are going to be getting smaller and smaller, or I guess bigger and bigger negative, which would be like saying negative infinity. Again, you could say that the limit of h of x as x is approaching positive infinity does not exist. And that's it. That is how you graph rational functions.